All right, Pre-Cal Chapter 7, Section 2. Let's see what we have. Matrices. I think all of us have seen matrices before. Matrix has rows to them. So here are the rows to matrices, just like if you're in a spreadsheet like Excel. Here are the rows coming across. It has columns. Columns are the things that stand up and down, just like the columns on a building. So we have rows and a column. The number of rows, and if they say M are the number of rows, so I have M rows here, and N are the number of columns, I have N columns, there we go, rows and columns, then we call it an M by N matrix. If I have a 2 by 3 matrix, I have 2 rows and 3 columns. I want you to understand this notation right here. Each of the entries or the elements in a matrix, each value in a matrix, is identified by its row column position. So if we look at this, A sub 12 means I'm in row 1, column 2. First number's the row, second number's the column. So if I say A sub 23, it means second row, third column. It's a position. So A sub ij, I, row I, column j. So it identifies a position in it. So each of the values that we put in, they are elements or they are entries. We have the I number is the row subscript. The J number is the column subscript. The order of the matrix, sometimes called the dimensions of the matrix, how many rows by how many columns. If you have a square matrix, it means you have what? Square matrix. I just give you a hint in what I wrote. Rows and columns are the same. It's square. 3 rows, 3 columns. 4 rows, 4 columns, etc. Equal matrices means that every corresponding element or entry is the same. 2, 3, 7, 1, 2, 8. What's the order of that matrix, by the way? Ooh, I'm getting too consistent. It's a 2 by 3. 2 rows, 3 columns. If it equals another matrix, it means all corresponding values have the same value to it. So I was real creative there. What's X? 8. Yeah, that's all it means to be equal matrices. So right down here, determine the order of the matrix. 2 by 3. Hope we have 2 by 3 out of our system. Order of this matrix, 4 by 2. Order of this matrix. So this would be called also a what kind of matrix? A square matrix. Moving on. If we are going to add matrices or if we are going to subtract matrices, you simply add or subtract the corresponding elements. Row 1, column 1 plus row 1, column 2. Row 1, column 1 plus row 1, column 1. I said it wrong. Row 1, column 2 plus row 1, column 2. You just add the corresponding things or subtract the corresponding entries or elements. So looking at this, matrix A gives the mean SAT verbal score in 6 New England states over the time period from 2001 to 2004. Matrix B gives the mean SAT mathematics score. So this is the one that we're interested in, right over here from 2001 to 2004. Express the mean combined scores for the New England states from 2001 to 2004. Well, they're already the averages, they're already the mean. So if I want the combined scores, we simply need to do A plus B. So if we took, let's take this one. So I am in, let me use A sub, identify that location for me. 4, 3, row 4, column 3. I would add it to, did I find the same spot? I think I found the same spot. B sub, row 4, column 3, 43. So if I did that, that should equal this number. 522 and 521, 1043. Sure enough, it works out. And you would obviously have to do it for every single one. Addition and subtraction of matrices, very straightforward. That's how it works. Scalar multiplication. When we talk about scalar multiplication, we're saying we're multiplying a matrix by a number. Consumer Advocacy Group has computed the mean retail prices for brand name products and generic products. Don't know if you've done much comparison shopping. Go to Walmart and you can see Walmart brand, great value, and then all these other major brands, whatever they are. The prices are shown in this 3x2 matrix on this page. So store A, B, and C, brand name price, generic price. City has combined sales tax of 7.25%. Construct a matrix showing the comparative prices with sales tax included. So why are they multiplying everything by this number? One is the original 100% plus the 0.0725, which is 7.25%. So if I multiply this 1.0725, I am going to, essentially you're distributing times every single thing, etc. And we have our solution right over here. So multiplying by a scalar, very straightforward as well. A zero matrix is just what it sounds like it is. It's a matrix filled with zeros. Doesn't matter the order of it, zeros in it. Additive identity. Let's pick up some definition of terms, and I'm going to use numbers first to remind us. 2 plus its additive identity will equal 0. Hang on a second. I just said that wrong. Additive inverse, additive identity. Oh, yeah. 2 plus... I went blank. I can think of the multiplicative identity, but I went blank on the additive identity, which I think is 0. Where am I? I am on 581. Is that where I am? That is where I am. Additive identity. Yes. All right. I didn't lose all my marbles. 2 plus the additive identity equals 2. What would I be adding to 2 if it stays the same? 0. So if I'm talking about matrices, the additive identity is a 0 matrix. Equals the same thing. If that's matrix A, I still equal matrix A when I'm done over here. Additive inverse, that's what I started to write a minute ago. 2 plus the additive inverse gives me the additive identity. What do I have to add the 2 to get 0? Negative 2. It's the opposite sign of it. So if I have matrix A, I would add the negative of matrix A in order to get my 0 matrix. I'll go ahead and put them in these little brackets. Put that bracket in the wrong spot. The negative needs to go on the outside of it. Brackets are going to be the symbols that we use around matrices. The product of matrices. Maybe in your memory from Algebra 2, you remember about finding the product of matrices. Matrix multiplication is not like addition or subtraction. I can't just multiply the individual little parts. We have to multiply the row times the column. In order to get the product, to get this C I sub j, in order to get that answer, I have to take the row product plus the row times the column, product, plus row times column product, all the way across. Let's see how it works right down here. If I'm going to multiply these together, I take the row 1 position times the column 1 position, 1 times 4, plus, then I take the second one times the second one, 2 times 5, plus, then I take the third one times the third one, 3 times 6. And since this only has 1 row and 1 column, I'm done multiplying these together because I've multiplied every row by every column. 4 plus 10 plus 18, answer 32. What is the order of this matrix? That is a 1 by 3 columns. What is the order of this matrix? 3 rows by 1 column. You may recall from past courses, if the middle numbers match, I can multiply them. Well, they do match here, so I can multiply these together. The outside numbers tell me the order of the answer. It's a one-by-one solution. One row, one column. That should be in bracket symbols because that is a matrix. It's just one number, but it's a matrix. So, coming over here, find the product if it is possible. What's the order of matrix A? 2 by 3. What's the order of matrix B? 3 by 2. Is it possible? It is. It's going to be a 2 by 2 matrix when we are done taking those outside numbers over there. So, if I am going to do this matrix multiplication, let me copy them. 2, 1, negative 3, 0, 1, 2. Multiply it by 1, negative 4, 0, 2, 1, 0. I am going to have a 2 by 2. I'm going to have 2 rows. I'm going to have 2 columns. I am even going to put little parentheses. 2 rows, 2 columns. That's what I'm going to get out of it. We are going to take the first row times the first column, a number at a time. 2 times 1, 2. Move down 1 times 0, plus 0. Move down negative 3 times 1, minus 3. That will be my first answer. And then I stick with the first row, and I just move over to the second column. So first number is 2 times negative 4, negative 8. Now notice something. This is row 1 times column 2, and where is my answer appearing over here? Row 1, column 2. Keep going. I did 2 times negative 4. 1 times 2 is a 2. Negative 3 times 0 is a 0. And so now I can come back down to row 2. It's nice if your paper did this. Back to column 1. So my first value, 0 times 1, 0. I'm in row 2, column 1, where my answer goes. 1 times 0, 0. 2 times 1 plus 2. And last column. So 0 times anything is 0. 1 times 2, positive 2. 2 times 0 is a 0. Now I can write my answer. First number, negative 1. Let's go across the row. Negative 6, second row, 2. 2. Is it a 2 by 2? Yes, it's a 2 by 2, just like we expected. Try another one right down here. Order. And we're done with this one. We hope we don't have very many of those, obviously, on homework because they're boring. Matrix multiplication. A florist makes 3 different cut flower arrangements for Mother's Day. 1, 2, and 3, each involving roses, carnations, and lilies. So we have a rose, 3 different arrangements, carnations, 3 different arrangements, and lilies, 3 different arrangements. Matrix A shows the number of each type of flower used in each arrangement. Oh, sorry, I read it wrong. In arrangement 1, we have 5 roses, 6 carnations, and 4 lilies, etc. In arrangement 2, they have their combination. The florist can buy his flowers from 2 different wholesalers, wholesaler 1 and 2, but wants to give all his business to either one or the other. The cost of 3 flower types from the 2 wholesalers is shown in matrix B. So the rose, carnations, and lily prices, $1.50, $95, $1.30, etc. Construct a matrix showing the cost of making each of the 3 flower arrangements from flowers supplied by the 2 different wholesalers. Well, I do know my cost is going to be number of flowers times price. Now, I want you to notice a minute, if I took the number of flowers times price, let me just move matrix B up there so I have A times matrix B because I want flowers times price. Let's see what happens when I do this. I have my 150, I have my 0.95, I have my 130. We need to make sure we're multiplying together what we want to be multiplying together. Just because I have 2 matrices doesn't mean it works out all perfectly. This stands for rose, carnation, lily, and this is wholesaler 1 and wholesaler 2. So if I go to multiply these things together, I would multiply row times column. Now I do have 3 numbers times 3 numbers, so I'm good there. I am multiplying 5 roses times the warehouse price of number 1 for roses. Then I'm multiplying 8 roses times the warehouse price of what? Carnations. This isn't working. Now my first one, I was okay. 5 roses and warehouse 1, they're $1.50. But then 8 roses times carnation price, that's not going to give me the answer I want. I need to rearrange that second matrix. So let's come down here. I have my rose, carnation, and lily matrix A just like we had again. Then they took this matrix B and they flipped the rows and columns. So what used to be the rows of the flowers became, oh, I'm going to take the first one, 5. Oh, did they just flip that one? All right, I'll do it their way. I was going to flip the second one, but they flipped the first one. So they took and flipped this one. So if, and they kept the second one the same. If I multiply these together, does it work now? Row times column. So this would be rows number times rows price. Carnation number times carnation price. Lily number times lily price. Ah, that will give me my warehouse 1 total cost. Go to your calculators. We are going to do 2 things with your calculators. If you have other stuff hanging around, clear it out. Let's find our matrix, which is right below the math button, above that x to the negative first. So here I have matrices. We are going to do matrix A as this original one back here for a minute. If I can pull that back. So we're going to do this original one. Hit enter on matrix. Oh, sorry. Go back to your matrices. I told you the wrong button. As soon as I can get rid of stuff. Second matrix. There we go. Go over to edit. I need to edit matrix A. I have to tell us its order. What's the order of matrix A? 3 by 3. Now I can enter in and it will go by rows. So 5, 8, 7, 5, enter, and it runs across the row. A, enter, 7, enter. Then it jumps to the second row. 6, 6, 7, 4, 3, 3. And by the way, oh, I missed it. When you are entering it, notice it tells you the row and column that you are in. 3, 3. All right. I need to go back and enter matrix B. I have to, and your operating system may be newer, but I have to quit and then go back to matrices. I can't go to matrix at that location, or it tries to stick a matrix inside a matrix. Now I go back to edit, and I'm going to choose matrix B now. And let's do this original one, the warehouse values. So what is it? It's a 3 by 2, isn't it? All right, have it all entered. I have to quit again. If you don't quit, it tries to do your next operation inside that matrix still. Now, what we decided was we needed to flip the rows and columns of matrix A. That's called the transposition of matrices. We need to transpose matrix A. Transpose matrix A is written that way, times matrix B. So I can do that on the calculator. I can go back to my matrix menu. I am going to choose matrix A, so I just hit enter. I have chosen matrix A. Now I have to go back to my matrix menu, arrow over to math, and notice that choice 2 is transposition of that matrix. So when I hit enter, it doesn't show me the matrix, but it will do the matrix transposition. Times, you don't have to hit times, it understands it. Now I need to do matrix B. So I go back to the matrix, I select matrix B, and I say enter, and it says, here's the answer of the multiplication of the transposition of matrix A times matrix B, which hopefully matches. What did I do wrong? Did you get it? So did I. I entered a number wrong somewhere. If you did what I said, not what I did, evidently, you will get the solution down here, which will stand for, so I have my number 1 is arrangement number 1 and warehouse number 1 prices. So that's going to be arrangement number 1, warehouse number 1 price. Arrangement number 2, warehouse number 1. Arrangement 3, warehouse 1. So this is warehouse 1, this is warehouse 2. If you wanted to know what is going to be the total, you would add them up. You would add them up and you would figure out, should I order from warehouse 1? Should I order from warehouse 2? So they just wanted to construct it to show the prices for the different wholesalers. But if you added it together, you could then figure out which one was the cheapest one. Identity matrix. An identity with numbers, if we're talking about multiplication, what would I multiply 2 by so it stays 2? 1. The identity is the thing that leaves the number staying the same. And the identity for real numbers in multiplication is 1. 3 times 1 is 3. 7 times 1 is 7. If we're talking about matrices, we have to have a square matrix to have an identity. And notice what's consistent about every single one of these. They have ones that are on this diagonal, top left to bottom right. Everything else involves zeros. That is the multiplicative identity for matrices. Depending on how big your matrix is, you pick the right one. So if I have an identity, if I go A times B, it's the same answer, whoops, inverse, jumped ahead of myself. An inverse, let me use numbers. 2 times what equals 1, the identity. What would I multiply 2 by to equal 1? 1/2. 2 and 1/2 are multiplicative inverses of each other. 1/2 and 2, multiplicative inverses of each other. Doesn't matter the order I would multiply these together, I would get the multiplicative identity. Matrices works on that same principle. Matrix A times matrix B must be the same answer as B times matrix A, and that answer must be the identity. So if that is true, that is an inverse. So if matrix B is the inverse of matrix A, and here's the notation for inverse, A inverse. That's not an exponent. That is the inverse notation. Some matrices have inverses, some matrices do not have inverses. Numbers always have inverses. I could give you any number and you could tell me what the inverse was. But matrices do not always have inverses. If it has an inverse, it's called non-singular. It's a non-singular matrix. You'll need to remember the term. If it does not have an inverse, it's called a singular matrix. Verifying that we have inverses of each other. I'm going to do it by hand because, quite frankly, it's faster doing it by hand than entering it in your calculator. If I verify I have an inverse, I need to take A times matrix B, and it needs to give me the identity. Then I need to take B times matrix A, and it gives me the identity. Why do I have to do it both ways? we're going to learn that matrix multiplication is not necessarily commutative, it is called. With numbers, 2 times 3 always equals 3 times 2. Real numbers are commutative under multiplication. But matrices, that's not true. A times B does not always equal B times A. So if I do that multiplication, 3, negative 2, negative 1, 1, times matrix B, 1, 2, 1, 3, and I get my solution out here. Now they're both 2 by 2, so my numbers all match. So row times column, 3 times 1 is a 3, negative 2 times 1 is negative 2. Sticking with my first row, 3 times 2 is 6, negative 2 times 3 is negative 6. Moving to my second row, negative 1 times 1, negative 1, 1 times 1, positive 1, and negative 1 times 2 is negative 2, 1 times 3 is positive 3. I do my 3 minus 2, that's a 1, 6 minus 6 is 0, there's a 0, there's a 1. I get the identity. That echelon, we call it, of ones. Doing the reverse order, matrix B times matrix A. You'll be asked in some of your homework to verify that two matrices are identities. This is what you do to verify that two, not identities, are inverses. They need to give you the identity when you multiply them in both ways. So, first row, 3 minus 2, 3 minus 2. Negative 2 plus 2. So this work is our verification. Second row, 3 minus 3. And negative 2 plus 3. 3 minus 2, 1, 0, 0, 1, check. I verified. They are inverses of each other. Determinants. Every square matrix has a determinant. You learned this back in Algebra 2 as well. We use determinant bars. Notice it's not a bracket. I don't square it off at the top and bottom. That means determinant. Here's how it could be written, determinant of A, or it could be written this way. And the formula is right here. A times D, I multiply these values together. Minus, always minus, B times the C. You could go C times B. They're numbers, so the order you do it doesn't matter. So how do I find the determinant of 2, 3, negative 5, and 7? Well, I would take 2 times 7, 14. Minus negative 5 times 3 is a negative 15, so I'm really adding. 29 is the determinant. The determinant is used in different functions. And one of those, and I hope some of you who are working are paying attention to me because I try to be real patient, but when you ask me questions and you weren't paying attention when I was teaching it to you, like I say, I try to be patient. If I want to find the inverse, I use the determinant. The determinant has many uses. One of them is this. And this is an inverse of a 2 by 2 matrix. So if I want to find the inverse of this matrix, A, B, C, D, 1 divided by the determinant. That's the determinant formula. 1 divided by the determinant. And then this matrix, I need to do some rearranging. This diagonal, what has happened to that diagonal? Switch the locations. This value, the C and the B, what has happened to them? They what? The change signs, the negative of the original. So they change signs. So it says, prove that this matrix B is singular. What does that mean? Has no inverse. Oh, it says it here. That is, A is no inverse. So let's figure out how would I prove it has no inverse? Well, let's look at this formula. What can I not divide by in math? 0. That tells me if the determinant is 0, then it would have no inverse. If the determinant of matrix B is 0, it can't have an inverse because I couldn't do that process up there to find its inverse. So 6 times 1, 6. Minus 2 times 3, 6. Equals 0, checks. It has no inverse. That's all it is. Now, I want to find the inverse of this matrix up here. Your book doesn't give you much practice at doing that. So if I have that matrix 2, 3, negative 5, 7, and I'm asked to find the inverse of that, 1 divided by the determinant, that's where we start. Well, we already figured the determinant was 29. 29 times the matrix, and we need to rearrange our order here, so my 2 and 7 become 7 and 2. Negative 5 becomes a positive 5. Positive 3 becomes a negative 3. I would then do what with this fraction 1/29th? Distribute, multiply it in, so that I would find the inverse is 7/29, negative 3/29, 5/29, and 2/29. That would be the inverse of matrix. Oh, that wasn't matrix B. We'll call that matrix A right up here. If that's my matrix A, we just found the inverse of that matrix. If we are finding determinants of larger matrices, they have to be square, then that 2 by 2, it's a more involved process. The 2 by 2 determinant process, pretty simple right there. We like those, they're nice and fast. But they're a little boring, so we like these too. Couple more definitions. We need to know what the minor is of a determinant and what the cofactor is of a determinant. So, the minor is this. If I have a square matrix, this one happens to be a 3 by 3 matrix, and we are going to find its determinant, they are using the second row. You can use any row, they've chosen the second, you can use any row, or you can use any column and follow the same pattern or formula, and you can find the determinant. So what we do is we take this element, a sub 21, that is going to be multiplied by its minor. And then a sub 22 is going to be multiplied by its minor. And then a sub 23 multiplied by its minor. So how do I do that? Well, that first part, the cofactor, negative 1 raised to the exponent, that is the sum of the row and column you are on. I and J are the row and column, times the minor determinant that is left. Let me go through the process. So if I'm going to do this, it means back here, a sub 21, there it is. I'm going to take that number. Then I'm going to take negative 1 raised to the, well, it's in the second row, first column, 21. 2 plus 1 is 3. That's where we get that third power from. Then the minor determinant, or the minor, if I cross off the row and cross off the column that this entry was from, this element was from, I am left with the minor. A sub 12, A sub 13, A sub 12, A sub 13, A sub 32, A sub 33. I'm left with that minor. And we repeat that process 3 times because I have 3 numbers. It's done once here, it's done once there, it's done once there. And then we simplify it. And these minor determinants are 2 by 2s, so I do that multiply down minus multiplying up to get the determinant of that. And when we're all done, eventually we get that determinant out of it. So we're going to find some determinants. Determine whether it has an inverse. If it has an inverse, we are going to figure out what that inverse is. We determine whether it has an inverse by checking to see if the determinant equals what? equals 0. And what does it mean if the determinant equals 0? No inverse. So let's try this one. 3 times 2, 6, minus 4 times 1, which is 4, which gives me a 2. I have a determinant. Yes, I have a determinant of 2. Yes, I have an inverse. So we are going to find the inverse of matrix A, which is going to be 1 divided by 2 times the matrix. Tell me the diagonal going down to the right. 2 and 3. Tell me the numbers coming back up. -4, -1. We have to multiply it in, so I'm just going to be taking 1/2 of everything. So 2, -1/2, 2, 3 halves. I have found my inverse. No problem. Thank you. -2. Now we are going to check the determinant of matrix B. When you do the determinant, I mentioned you can take any row, any column. If you see a 0, pick that row or pick that column, because you're going to be multiplying by -1, then multiplying by 0. Oh, that's all going to disappear. What's that? Boy, 2 mistakes in the same problem. Are the rest of them right? -1/2, 3/2. All right, 50%. Didn't pass that one. Let's try this matrix now, working with row 3 on that formula that we saw on the previous page. So here's how it works. I'm going to start with that -1. -1 times -1 raised to the, what position is this? Row 3, column 1. So if you add 3 and 1 together, you get a 4, fourth power. Times the minor. So I need to cross off the row and column that -1 is in, and what is left is 2, -1, -1, 3. Plus, and we're going to move across this row. Now I know that will be 0 when I do this, but I want to go through the pattern so that we remind ourselves how it works. Whatever that element is, 0 times -1 raised to the, what position is this? This is 3, 2, so it would be to the 5th. And I'm going to explain in a minute what all these -1s are doing for us. In your mind, cross that off, tell me what I'm going to get. If I go across, depending on how you're reading it, 1, -1, 2, 3. If I cross off the row and the column and the row and the column, 1, -1, 2, 3. Plus, now I use the 1 times -1 raised to the 6th times its minor, 1, 2, 2, -1. Now, this is all 0, so I don't have to worry about that thing. What's -1 to the 4th power? 1. So 1 times -1 is just -1. Times this determinant. Well, 2 times 3 is 6, minus -1 times -1 is a 1. That's the math here. 0 plus -1 to the 6th is 1. 1 times 1 is 1. Times its determinant. 1 times -1, -1, minus 2 times 2 is 4. So when I simplify this, what's that? -1 times -5? So it'd be 5. That's 1 times -5. 1 times -5 is... Did we do the math right? No. That's a -5. 6 minus 1. 6 minus 1 is 5, right? -1 times 5, -5. So this equals -10. Does it have an inverse? It does. How do we find the inverse? We didn't teach you how to find the inverse by hand. So guess what we do? Go to your calculators. Let's come back to this lovely matrix B right over here. We'll go to our matrix. We need to edit, and I'm going to call it matrix B. You could choose any of them. I'm going to hit enter there, Now, the last time I used it was a 3 by 2. This is a 3 by 3. 1, 2, negative 1. 3. Probably should erase some of these markings so that you could read it. Make sure I entered it right. I think I did. I need to quit out of this. But I'm going to go back to my matrix. I'm going to select this matrix. Now it was matrix B. I'm going to select that matrix and inverse. X to the negative first. That's the inverse button. The inverse of matrix B. Enter. Now they give you these decimals. Sometimes we don't want decimals. Let me back up a minute and do the same thing with one slight change. Matrix, I'm still going to choose matrix B. I'm still going to choose the inverse, but before I hit enter, I'm going to hit my math button, and choice number 1 says give me the answer as fractions. So when I hit enter, there we go. 1/10, 1/5, negative 1/2. Now that ... is because it doesn't fit on my screen. If I just arrow to the right, there's the rest of it fitting on the screen over there. So let's see if I did it right. Oh, sure enough, right over there. There's my inverse to it. Now you actually have determinant capabilities on your calculator as well. We got a negative 10 back here. If I come back to my matrix and I say I'm going to select my matrix, whoops, not yet. I want to do math. Notice choice number 1 is determinant. I want to find the determinant of, go back to my matrix, B. I'm going to close my parentheses to be consistent. And they say, hey, sure enough, it's negative 10. You need to be able to do it by hand on those up to 3 by 3s. If they give you anything larger than 3 by 3, the calculator is just fine. Finding an inverse of a 3 by 3, we're going to do it on the calculator. We don't have any hand formula that you were given to you. So it's going to be a combination here of calculator stuff, by hand stuff. Properties. When we are dealing with matrices, the commutative property of addition is good, but not multiplication. You can switch the order you add matrices, you get the same answer, or subtract, but you cannot do it with multiplication. The identity property, which means I don't change it. So if I'm adding, I'm going to add the 0 matrix. If I am multiplying, then I am going to have to multiply by that matrix with the diagonal of 1s. That is the identity. The distributive property works with matrices. So you can see down here, I can distribute from the left, distribute from the right. The distributive property works with matrices. The associative property works. I can group them, addition or multiplication, in different ways. As long as I'm not rearranging them, that's commutative. I can group them differently, I get the same answer. Inverse property, if it's addition, my answer is 0. If it's multiplication, my answer is the identity. Number 9, the last thing. They give you just a little peek into some of the uses of matrices, and there are many uses, and they're just giving you kind of a peek into it here. We can use matrix multiplication with points on a plane, and we can do transformation to those points on a plane. And what I mean is, if you have points on a plane, if I just have 3 points, the connection of those 3 points would make a triangle. Meant to be a solid line, the connection would make a triangle. I can take that triangle and I can reflect it across the y-axis or reflect it across the x-axis, just like we do with formulas. Or I can take that triangle and I can rotate it. All of those things can be accomplished with matrices, and they're just giving you one example. They say, prove that the image of just a point under reflection across the x-axis can be obtained by multiplying with this matrix. So if I have some point that I want to reflect across the x-axis, well, I'm going to choose this point right here. And that point happens to be the point x comma y. Any x, any y. If I reflect it across the x-axis, it would end up in the same position relative to the x-axis down here. Tell me the ordered pair using x and y ideas. X negative y. It's still over x, but now it's going to be down y. That should be my answer if I have reflected a point across the x-axis. So, if I take point x, y, we're going to do it like a matrix, x, y. That is a matrix 1 by 2 in order. We are going to multiply it by the matrix that they say is supposed to do a reflection. 1, 0, 0, negative 1. This is a 2 by 2. Is multiplication defined on those orders? Yeah. And when I'm done, what's going to be the order of my answer? A 1 by 2. An ordered pair. One column, or one row, 2 columns. It's going to be an XY answer. So this should all work for me. So if I do my multiplication here, row times that first column, x times 1 is x, y times 0 is 0. Second column, x times 0 is 0, y times negative 1 is negative y. If I simplify that, I get x, negative y. Sure enough. Your proof is just your work. It worked out. Again, they're just hinting that matrices can be used to do all these transformations. If you have the right matrix, it'll reflect it, it'll rotate it, etc. All right, you've got the syllabus.